Have you ever pictured those windows made of like transparisteel from Star Wars, or maybe transparent aluminum, straight out of Star Trek? That classic sci-fi idea, seeing right through solid metal. It's always felt like, well, pure fantasy. But here's the question we're tackling. Is science actually catching up? Is this stuff becoming real? Today, we're going to do a deep dive into the surprising reality behind transparent metal. We'll start with why metals usually aren't see-through, the basics. Then we'll unpack some really interesting experiments, ones that can be a bit misleading sometimes. And finally, we'll get into how real-world innovations are pulling these amazing materials out of sci-fi and into our actual lives. Seriously, think about it. This could change everything from your phone screen to aerospace tech. So let's get into it. Okay, let's really unpack this first bit. We've all seen aluminum foil, right, or a copper wire. They're obviously solid, opaque, but what is it fundamentally about metal that stops you seeing through it? What's the actual science there?
It's actually pretty cool how it works. It really all comes down to the electrons inside the metal. See, metals are unique because they have these things called free electrons. These aren't stuck to just one atom. They kind of move all through the metal, almost like a gas or an electron plasma. And this electron plasma, that's exactly why metals conduct electricity so well. Now, these free electrons, they also have a specific energy level, a frequency where they really react strongly to light hitting them. They absorb it powerfully. We call that their plasma resonant frequency. So for light with low energy, like radio waves or microwaves, this electron plasma just bounces them right off, almost perfectly. But then for light in the middle range, like the visible light our eyes see, that's right near the plasma resonant frequency. And because it's so close, the light gets strongly absorbed. It just can't get through. Think of it like trying to shout across a really loud concert. Your voice just gets drowned out, right?
Okay. Yeah. So the electrons are just soaking up the light energy.
Exactly. That's the main reason metals block visible light. Unlike something like glass, where the electrons are held tight and don't really interfere in the same way. What's also interesting, though, is that for light energies higher than visible light, the electron plasma actually does become transparent again. And, in real metals, things are a bit more complex. Electrons can jump between different energy levels or orbitals. That slightly shifts the plasma resonance frequency, which is why you get colored metals, like gold.
Gold, right. It looks yellow.
Yeah, because it absorbs the blue and green parts of the light and reflects the yellow. But generally speaking, pretty much all metals behave similarly with visible light because their electron plasmas are pretty similar. So yeah, truly transparent metals in the visible range. You just don't really see them normally.
That makes a lot of sense. But then you see these videos online or hear about experiments like that transparent sodium demonstration. It really looks like you're seeing a metal just turn clear. So if it's not the physics you just explained, what's really going on there? How do they get that clear effect?
Yeah, that's a great one to bring up because that demonstration, it definitely causes some confusion about transparent metal. What you're actually seeing in that sodium demo is a very fast chemical reaction. When you put sodium metal in water, its outer electron, which is only weakly held, jumps off pretty easily. It combines with protons from the water, and boom, you get hydrogen gas bubbling off. But what's left behind isn't sodium metal anymore. The reaction forms sodium hydroxide salt, and that substance is transparent.
Sodium hydroxide, like lye.
Exactly. And here's the key part. The reaction is so intense, it generates a ton of heat. So the sodium hydroxide that forms is actually in a molten state. It's a liquid, clear drop of this hot alkaline stuff.
Molten salt. Oh.
Right. And the filter paper they often use, that actually helps slow the reaction down just a tiny bit. It lets the ions move and react more gradually, so you get a brief moment where you can see that clear molten drop form before it all goes boom.
So it looks transparent, but it's absolutely not transparent metal. It's a different chemical altogether.
Precisely. It's crucial to understand that. It's a metal hydroxide, not a metal. And then, like you mentioned, what often happens next is what's called a Coulomb explosion. That molten sodium hydroxide is denser than water. It melts through the paper, hits the water underneath. And because it's superheated, it vaporizes the water explosively. A much bigger, uncontrolled burst. Very dangerous stuff, actually.
Okay, so definitely a cool reaction, visually dramatic, but not actually transparent metal, which, brings us back to the question, is there any such thing as a truly transparent metal? The sources mentioned another type, one that actually is metal. How on earth does that work?
Yeah, this is where it gets interesting, and it's about nuance, really.
Right.
When light hits something that absorbs it, it doesn't just vanish instantly at the surface. The amount of light that actually gets into the material drops off exponentially as it goes deeper.
Okay.
Like it fades out quickly. Exactly. So this means that if you have very, very thin pieces of metal, well, a noticeable amount of light can actually make it all the way through. There's an example in the sources, I think, of a piece of aluminum foil that's only about 100 nanometers thick.
100 nanometers. That's incredibly thin. Like, what is that, a few hundred atoms thick?
Something like that, yeah. Super thin. It's usually attached to a piece of plastic for support. They make it using a process called vacuum deposition. Basically, you evaporate the metal in a vacuum chamber, and it condenses onto the plastic as this ultra-thin film.
And what does it look like?
Well, it still reflects some light, so it looks kind of grayish and metallic. The reflection is dimmer than normal foil, though. But the key thing is, because it's so thin, a surprising amount of light also passes right through it. They mention shining a green laser through it. Imagine seeing that beam go straight through something that looks like shiny metal foil. It looks really weird.
Wow. Okay, so that's a true transparent metal then.
Yeah.
Just an incredibly thin version of it. It really makes you think differently about what transparent metal could even mean, doesn't it?
Exactly. It's not always about changing the fundamental nature of the metal. Sometimes it's about the form factor.
Right. Now, let's maybe shift gears a bit. There's another whole category the sources talk about, things often called transparent metal, but they're actually ceramic compounds made with metallic elements.
Yeah.
And the most famous one, the one everyone brings up, is transparent aluminum.
Yes, absolutely. The stuff from Star Trek 4, right? Computer. Hello, computer.
Haha, yeah, that one. Scotty trading the formula for some plexiglass.
Well, the real-world transparent aluminum is technically called aluminum oxynitride. The commercial name is ALON. And it's important, like you said, to clarify. While it has aluminum in it, it's not pure metal. It's a ceramic. It's a complex mix of aluminum, oxygen, and nitrogen. Structurally, it's much more like a really, really tough kind of glass.
But it sounds incredibly strong.
Oh, its properties are seriously impressive. It's as clear as regular glass optically, but it's way stronger than typical safety glass or security glass. We're talking 3 times stronger.
3 times, wow.
Yep. It's bullet resistant too. It can apparently stop armor-piercing bullets. It handles extreme heat, big impacts, and compared to traditional bulletproof glass, it's much lighter and thinner for the same level of protection. Plus, you can polish it perfectly smooth, optical clarity.
So where is this stuff actually used now?
Right now, it's mostly in very high-end applications. Think aerospace manufacturing, military-grade bulletproof windows, protective domes for sensors on aircraft or missiles, things like that.
It really does sound like something out of science fiction. Like Star Wars transparisteel you mentioned earlier. How close is it, really? What are the limitations compared to, the fictional stuff?
That's a fair comparison. The capabilities are amazing, but yeah, there are still big differences from fiction. Cost is a huge one. A lawn is incredibly expensive, like $10 to $15 per square inch.
Ouch. Okay, not replacing window panes anytime soon.
Definitely not. And manufacturing it at large scale is really difficult. There are often trade-offs, too, between maximizing toughness and maximizing optical clarity. And while it's tough, it can still be brittle compared to, say, metal. Shaping it into complex curves is also a challenge. And just quickly, there are a couple of other similar materials worth mentioning. There's magnesium aluminate spinel. It's another synthetic crystal, sometimes called spinel. It's maybe slightly clearer optically than ALON, a bit easier to make in thin sheets. And it transmits infrared light well, which is good for sensors.
Okay.
And then there's synthetic sapphire. That's basically a single perfect crystal of aluminum oxide. It's even harder than ALON or spinel, but it's also more brittle and even more expensive to make in large, flawless pieces.
So incredibly strong, incredibly clear, but also incredibly expensive and tricky to make. That seems to be the pattern.
Pretty much, yeah. That's been the state of play for these advanced ceramics.
But speaking of those manufacturing challenges, you mentioned something earlier. There's been a really exciting recent breakthrough, something that might tackle those cost and difficulty issues.
Yes, this is where things get really interesting for the future. There's been a discovery by scientists, I believe, from Ateneo de Manila University in the Philippines. It's focused on transparent aluminum oxide, or TaOx. Now, aluminum oxide itself isn't new. Synthetic sapphire is a form of it. But this TaOx has that great combination: durability, heat resistance, optical clarity, literally a metal-based material you can see through, much like ALON. But the way they made it is the game changer.
How so? What's different?
Well, traditionally, making these materials involves really expensive, complex processes, high-powered lasers, vacuum chambers, nasty hazardous acids, things like that. High energy, high cost. This new technique is called droplet scale anodization. They figured out how to transform aluminum into this transparent Ta-ox using just tiny microdroplets of acid and an electric current.
Microdroplets, how does that work?
The secret sauce seems to be something called electrowetting. It's a way of using an electric field to precisely control and manipulate these tiny liquid droplets. It allows them to perform these chemical reactions like anodizing the aluminum very precisely, very efficiently on a tiny scale without needing the massive, costly equipment.
Whoa. So what does that actually mean for us? If it makes TLOX much more affordable and accessible, like the sources say,
Right.
and it keeps the strength and durability, that sounds huge.
It absolutely is potentially huge. This kind of breakthrough could open the door to using these materials much more widely. Think about your phone screen. Imagine one that's way, way stronger, much more scratch resistant than what we have now. You might not even need a screen protector anymore.
I'd love that.
Right. Or think about ultra-durable clear coatings for vehicles. Cars, sure, but also spacecraft, aircraft, protection against wear, heat, impacts. It could also be really important for enhancing optical sensors. Things used in AI systems, like self-driving cars, need clear, tough protection for their lenses and sensors. This could make them more reliable, more resilient.
So with this kind of manufacturing innovation, that whole era of transparent, super strong, metal-like materials, it stops being a far-off dream. It could actually be on the verge of becoming, well, a widespread reality.
That seems to be the potential, yes. It's moving from specialized niches towards broader applications.
Okay, fascinating stuff. Now, there's one more material mentioned with a really evocative sci-fi name, transparent steel. But let's get straight to it. What is transparent steel, really? Is it actually steel?
Good question to clarify right away. No. Transparent steel is actually a brand name or a nickname for a specific product called Armour AP25, and critically, it contains absolutely no actual steel, or any other metal for that matter.
Ah, okay. So the name is just about the strength.
Exactly. The name comes purely from its steel-like strength and impact resistance.
Yeah.
What it is made of is a single layer of something called AR polycarbonate. That AR stands for abrasion resistant. It also has UV resistant coatings.
Polycarbonate, like Lexan, that kind of stuff.
Pretty much, yes. A very strong type of plastic. What's remarkable about this AP25 is its practical toughness for security. It's technically a non-ballistic grade, so it's not rated to stop bullets completely like ALON can be. But, and this is key, it's so strong that even if it does get hit by bullets, it won't shatter or break apart easily. It maintains its integrity.
So it still acts as a barrier even after being damaged.
Precisely. It offers the clearness and surface hardness kind of like glass, but it combines that with the virtually unbreakable impact resistance of polycarbonate. Plus, the coatings make it resistant to yellowing from sunlight, hazing, getting marred or scratched easily, and even resistant to chemical attacks. It's designed for a long service life.
And compared to transparent aluminum, I assume this is much more affordable.
Oh, vastly more affordable. That's the whole point, really. It's designed as a realistic, cost-effective alternative for commercial security. It acts as a really formidable barrier against forced entry. Think bats, crowbars, sledgehammers, other tools burglars might use. So it's ideal for security glazing in places like schools, hospitals, government buildings, religious centers, retail stores.
Places vulnerable to smash and grab, vandalism, rioting.
Exactly. Burglary, looting, storm damage protection, even delaying active shooter forced entry attempts by making it much harder and slower to break through windows or doors.
And it sounds like installing it is pretty straightforward, too.
Yeah, that's another big advantage. It's relatively lightweight and adaptable. You can retrofit it into or onto pretty much any existing door or window frame. Doesn't matter if the frame is wood or metal, old or new.
So you don't need to rip out existing windows.
Often not, no. It can be installed right over them or within the existing frame. And visually, it's quite low profile. It adds maybe about an inch around the edge, but because it's crystal clear, it doesn't really cut down your view or change how the building looks from the outside. You get serious security without making the place look like a fortress.
So, okay. You, our listener, have journeyed with us on this deep dive now. We've gone from the basic physics, why metals are usually opaque, to these fascinating ways scientists and engineers are achieving transparency. Through making metals incredibly thin, through these amazing ceramic compounds like ALON and the potentially game-changing TLOX, and even through these super strong metal-like plastics, the polycarbonates like transparent steel.
Yeah, and I think the core distinction to really hold on to is this. True, see-through elemental metals. Still mostly confined to those super thin nanoscale films. For now, anyway. But these transparent metal-like compounds, the ceramics, the advanced polymers, They're rapidly moving beyond just sci-fi ideas. They're becoming real, tangible, high-performance materials that are already making an impact in defense, in electronics, and in everyday security applications.
So thinking about all these rapid advancements we've discussed today,
Yeah.
from electrowetting making tealox cheaper to these next-gen ceramics, it makes you wonder, doesn't it? What other impossible materials from our favorite sci-fi stories might actually be closer to reality than we think? And maybe, how can understanding the science behind them, like we try to do today, help you separate the real possibilities from the pure fiction in the future?